Okay, let's have a look at the variations. That means the problems that we are looking at today. A couple of problems all pertaining to the underlying theme that they can be tackled using a breadth-first search approach. Let's have a look at the first problem called symmetric tree. That's 101 symmetric tree flagged as easy, and it reads as follows. Given a binary tree, check whether it is a mirror of itself, that means symmetric around the center. For example, this binary tree 1, 2, 2, 3, 4, 4, 3 is symmetric. Just by looking at it, it's basically like mirrored around the center. But the following 1, 2, 2, null 3 is not. And then it comes with some follow-up suggestions on either solving it recursively or iteratively, but that's beyond the scope of what we want to achieve. Let's have a look at the next problem. 301. Remove invalid parentheses, flagged as hard. Remove the minimum number of invalid parentheses in order to make the input string valid. Return all possible results. And the note, the input string may contain letters other than the parentheses, open and close parentheses. Example 1, input, open, close, open, close, close, open, close. So then the output would be open, close, open, close, open, close, and open, open, close, close, open, close. Example 2 is open, letter A, close, open, close, close, open, close. And then the output would be open, letter A, close, open, close, or open, letter A, open, close, close, open, close. Here we have the example 3, which results in an empty output, is close, open. So basically both parentheses will be removed. Next problem, 1091, shortest path in a binary matrix flagged as medium. In an n by n square grid, each cell is either empty 0 or blocked. A clear path from top left to bottom right has length k if and only if it is composed of cells with the numbering c underscore 1 all the way up until c underscore k, such that the adjacent cells ci and ci plus 1 are connected 8 directionally. That means you have like 1, 2, 3, 4, 5, 6, 7, 8. So vertical, horizontal, and the diagonals. C1 is at location 0, 0. That means it's in grid 0, 0. CK is at location n minus 1, n minus 1. So we assume that's a square grid. And then CI is located at RC. Then grid RC is empty. It means grid RC is 0. Return the length of the shortest such clear path from top left to bottom right. If such path does not exist, return -1. Now have a look at the last problem. 200 numbers of islands, medium. Given a 2D grid map of ones and land and zeros, water, count the number of islands. So that's basically like a find the connected components and give them an individual label. An island is surrounded by water and is formed by connecting adjacent lands horizontally or vertical. So in this case we've got like a 4 connected neighborhood. You may assume all 4 edges of the grid are all surrounded by water. So that's like a boundary condition to talk about. Example 1, input. Then we see an area that's basically 4 connected with each other. And it's like one island here on the top left corner with ones, and then the bottom right part is like all zeros. And then here we got like example 2. 4 ones in the top left corner, and then it looks like they are all diagonally connected all the way to the bottom right, but remember we only have like a 4 connected neighborhood, so that means that one in the prior to last row is an island in itself. So that main theme underlying to the problems that we just saw is breadth first search, and it's wonderfully explained in this tutorial from hackerearth.com. It's a tutorial on breadth first search with a lot of visualizations on it, so it's really worth going through it detail by detail. It basically explains the main idea of going from a starting node to all neighboring nodes at the same level, visiting all of them first before going to the nodes at the next level. So like in the example of a tree, you would go layer by layer. In the example of just like an arbitrary graph, you would go like closest neighbors, their closest neighbors, their closest neighbors. And the key idea of how to implement that, here also explained in pseudocode, but also further down in a language that we can actually use for implementation, C++, is use the STL queue for it. So for example here, we initialize a queue with the positions of our underlying data structure. Let's say, for example, the data structure is a tree, the data structure is a graph, or the data structure is a 2D array with neighbor structures. We would initialize like the starting position. We put our starting position into the queue, and from that starting position we would know what are the neighbors by like querying. We would query, for example, in the graph, we would know who are the edges from that node. In the tree, which are the children. In an arbitrary array, we would query the position and then go by the neighbor relation, say +1, -1, +1, -1, and then get our neighbor relation from that. The key idea is then to basically have an iterative approach where you look into the queue, take the first element of the queue, query its neighbors or operate on it, query its neighbors, and put those neighbors back into the queue, depending on some additional logic. And one key logic usually would be to see if you have been to that node already. Otherwise you might run into like an infinite loop by always, go from the first neighbor to the next neighbor, and then the next neighbor has the first neighbor as its neighbor, and you would like go back and forth by just pushing it back into the queue. So the idea is to also keep track of where you have been already by like having a visited flag, or keeping like a visited data structure in terms of like maybe the array when you visited your neighbors. Just flag it as visited or not visited. If not visited, then push your neighbor element, your child element, your connected element in the graph back into the queue and iterate on it. And once you iterate, you take the element from the front of the queue and perform your operation, and then you pop it from the queue. It's not longer in your queue of operations. And you operate up until your entire queue is empty, which then means you basically have operated all elements that can be accessed from your starting point. So to summarize, you have to have like a queue that you initialize with the starting point, and you really need to make sure that you have like a visited flag or a visited data structure that makes sure that once you have already taken out an element of the queue, that element does not enter the queue again. So let's have a look at the solutions, all applying our theme to those different problems. So in all 4 solutions, we will see an approach using the paradigm of breadth first search. And remember, that was implementing a queue, initializing it correctly, and then iterate on that queue, updating it up until that queue is empty. Okay, so the first problem was to find that symmetric tree. And sure enough, we will find a queue of tree nodes Q, and we push onto the tree node the root node twice, which is essential for finding the symmetry going on there. And then we basically always pop twice for the left, for the first symmetry, part of the symmetry, for the second part of the symmetry. So we pop those and call them left node and right node. And then as soon as they disagree, at one point we know already that's not a symmetric tree in itself. If they do agree with each other, so like if they are the same value, we keep continuing, seeing if their children are both valid, and we would push those children back into the queue. Remember, if it's symmetric, that means from the left branch we would go into the left child, and from the right branch we would go into the right child to test the symmetry. Same note goes for left branch as right child, as right branch as left child, which is that part here. And then finally, if both kids are zeros, so this is like some two of those corner cases, in that case you would also have to return false. And then you iterate all the way in your queue up until you have basically visited all elements, which again, in the case of a tree, gives us the luxury of not having to deal with a visited data structure, since we basically just go from top to bottom, and we are ensured that there's no cycle per definition as a tree in that graph. Once we have finished our queue with no false returns, we can assume that all conditions for a self-symmetric tree are valid, and then we can return true. Second part is remove invalid parentheses, which again was flagged as hard, so that already notes us that we have to have like some sort of helper functions that we look in here. So bool has valid parentheses, string of a certain string. We just like look in there and count our parentheses, and if it doesn't have the right parentheses, we can return false. And if the count of open and closed parentheses is the same, then we can also return true or false. In the main function remove invalid parentheses, we find again the theme of a queue that we work through. So in this queue, we push in the original string and then work on that string. Right? We pop the string, keep a visited data structure again. Remember, we have talked about keeping a data structure to make sure that we not visit the same element twice whenever we pop something from the queue and push it back in there. And then we look at that element and then run this helper function on it. And if it's valid, then we basically put it into a vector of valid parentheses, or like a vector of string, a vector of solutions, where we put that in. That means at least if one solution has been found, we can flag valid string found as true and continue. Otherwise, we will have to work on the string and then push it onto our queue. And we will continue that again up until our queue is empty, which in terms of breadth first search means from our starting point we have branched out all the way up until we reached the boundary of our observable universe in the data structure. Okay, next up is the problem of finding the shortest path in a binary matrix, which basically leverages the fact, since we are doing breadth first search, we go level by level, or we go basically increase distance by 1 with respect to our neighborhood relation. So as soon as we clear like one list of neighbors in that queue that all belong to, as neighbors to one starting element, we know that we've basically worked on all the elements that have the same distance, and then all the next elements that come back into the queue have distance +1, and so on and so on. So that means if we just keep Q operating on our elements, once we find an element that satisfies our final condition of, say, being the goal position where we want to go from our start position, that means we have already found our shortest path per definition, because we breadth first search our way down from the starting position. There's no shorter way than doing breadth first search. That's guaranteed. And that's basically all the magic behind it. So again, we initialize our queue. Here it's a pair of ints, since it's a 2D matrix. We do some edge cases that are worked out here. And of course, we have to make sure that we don't visit the same elements twice. If that's all in short, we basically go into our queue and operate on it up until that queue is empty. So that's like this key theme of while queue is not empty. Get the front element of the queue and look at the valid neighbors of it, which in our case was that 8 neighborhood of directions, which here nicely is defined as a vector of vectors direct, 1 0 0 1 minus 1 0 0 minus 1, etc. So we look through all those directions and initialize our positions in the array accordingly, and then if it's a valid position and you can go there, etc., then you push it back into our queue. And at one point we might have reached our destination. If not, we just keep searching. And here in this case, once we have reached our destination, n minus 1, we return actually the overall distance. So distance was actually what we kept track while doing our breadth first search. Distance of the start element is 0. It has a 0 distance to itself, and then from all its neighbors, it's just basically old neighbors distance plus 1. So if we start from 0, then all its neighbors have distance 1, and their neighbors have distance 2 to the starting element, etc. Up until we reach that lower corner in the matrix, and that corner has the distance n minus 1, which again per BFS definition is the shortest distance to the start. Okay, so that one has several solutions to numbers of islands, and you will find oftentimes there's a case where you can do interchangeably depth first search versus breadth first search versus other approaches when it's not critical, for example, to find like a shortest distance. A shortest distance would require breadth first search in that case. Here it's about just labeling those islands, and so that doesn't matter how long it takes us basically to find all those individual islands, even though of course we want to have like the best computation time, that's for sure. But you can use DFS and BFS interchangeably for that problem. However, we focus on BFS here, just again to find that underlying theme for our problem here. And the underlying theme here again is initialize a queue, work on that queue up until it's empty, and make sure that we don't visit the same element twice. We'll do exactly that. And we make sure whenever we encounter an island that we flag that island with an ID, and while we are at it, we increase an overall number of islands that have been encountered, and the overall number here is then tallied in answer, and that answer is incremented whenever we encounter like a new island that has not been flagged yet. Right, so when we have an island that has been flagged already, so there's an ij that's unequal 1, so either it's water, so that's 0, or it's something different than 1. In our case here it's flagged as x. And then we have found a new island. If we found a new island, then we increase our answer. And so whenever we hit a new island, we do like our breadth first search, just like find all the neighbors on the island and then flag them as being visited already. That's basically the whole magic behind it. Just basically to go through the key elements of the breadth first search is have a queue, initialize it with your starting position, and work on that queue. Pop the element on the queue and then put it back in, put the neighbor elements back into the queue, and then work so long onto the queue up until the queue is completely empty. And that's all to the underlying theme of breadth first search as a means to solve the problems that we have visited.